Ba ba da ba. All right, so here we are, take 2 of SDS-PAGE part 2. So we have already run our job. We have let the proteins migrate approximately halfway through the gel itself. Things of note. 1, the separation between all of your proteins is not going to be as great when you do not let the gel resolve for a huge amount of time. So the less time that you resolve your proteins, the less separation that you're going to get between those proteins. That's something to keep in consideration whenever we look at the results of our gel. So after running our protein gel and after removing it from our pieces of plastic in which the gel was cast, I transferred it into a small plastic container. Now, in that plastic container, I added our stain solution. The stain solution had a fairly simple composition. The stain solution was, just a second. Okay, where are we? The stain solution consisted of Kumasi blue, leave it, R250, acetic acid, and methanol. The staining process for the gel requires you to take this solution right here and incubate your gel in this mixture for the better part of 15 minutes, all the way up to 30 minutes or maybe even an hour. If you incubate your gel in the stain solution for longer than an hour, the destaining process is going to take even longer than it otherwise would. So there's almost a threshold that you don't want to go beyond this, because if you do, then you're going to spend a lot of time doing the second part of it. Now, after you've let your gel incubate in the stain solution, what you're going to do is rinse it off, then place it in the destain solution. Now, I'm not going to rewrite all of this, but your destain solution has a composition that is the exact same as your stain solution minus the Kumasi blue. The Kumasi blue R250 is actually the staining agent. Now, one thing that's worth noting is the Bradford reagent that we use is Kumasi blue G250 plus phosphoric acid and I believe methanol as well. Yeah, methanol as well. So you have, and water. But effectively, this Kumasi blue reagent binds to proteins. And so essentially what you're going to do is you're going to incubate your stain solution with your protein, or with your protein gel, allowing that Kumasi blue to bind to all different parts of your protein. Then what you want to do is rinse away all of the Kumasi blue that did not bind to your protein. And that's called the destaining process. Now, if you watch right here in this video, which I'm going to switch to right now, and unfortunately, I tried to film it direct on, but it's at an angle. So tilt your head for just a moment. And what you'll see is this very dark stain solution with your protein gels in there, shaking on what's known as an orbital shaker. You'll let this go on for the better part of 15 minutes. Then the next step in the process is to, I believe this is the right video. There we go. Take that stained gel and rinse it off with some deionized water. The purpose of this is really just to dilute out any of that excess stain solution, or dilute out as much of that excess stain solution as possible. So we'll pour it off or decant it, add deionized water, decant it, add deionized water, and do that maybe 3 times. And once you've completed that, then you're going to add to that your destain solution. So that's what a stained gel looks like. You can't really see anything in there. You can't really resolve any proteins from one another. So that's why you add your destain solution and you let it incubate for even longer. We did a stain for 15 minutes. I destained over the course of about 6 hours. Now, after that destaining has completed, that gives us the following image, which I do have to rotate a little bit once we get it opened here. Oh, no, it's already done. And actually, can I flip it clockwise or flip it on its x-axis? I'm sure that I can, but I'm not going to mess with it. Instead, I'm just going to change my share. So here is our protein gel. A couple of things to recognize about this protein gel. One is the ladder is on the far right-hand side of the gel. That's our molecular weight ladder. Now, this molecular weight ladder, what you should be able to see are a couple of different unique bands. Now, if you're looking at this and saying, well, I don't really see anything. I see 2 bands and then I see kind of a smear where Dr. Gray has written 3 red lines next to it. Your eyes aren't deceiving you, and I'm not telling you that your eyes are not deceiving you. What you're seeing is kind of the effect of a gel that's run at too high a voltage. Too high voltage. Now, whenever you run a gel at too high of a voltage, your resolution goes down. And whenever I say your resolution, I mean your ability to distinguish different bands from one another. Your quality basically deteriorates, and your precision, where you can see lines or where one protein sample ends and where the next begins, it's going to go down. Now, with all of that said, you will see on your final exam some practice or some questions that refer to an SDS-PAGE. Now, what I can tell you about this pre-stained ladder is this large band right here is, I believe this one's 120 kilodaltons. The one below it, I believe, is 95 kilodaltons. Then these 3 between there, I really can't distinguish between those. Now, what I would also like to say about this protein gel and this molecular weight ladder together is we need to think about how far we resolved our gel. Well, we ran our gel to about here, approximately halfway the length of the entire gel. So was there more room to let our proteins migrate? Absolutely. Had we done that, what we would have observed between this 120 and this 95 kilodalton protein is you would have seen greater separation. So run gel for a longer time will cause your resolution and your separation of proteins from one another to go up. So essentially your takeaway for this is if you want the best resolution, you should run your gel at a low voltage or a lower voltage, and you should run it for longer. Now, you're going to have to run it for longer by default by running it at a lower voltage because that electric current running through your protein gel, if it's not as high, your proteins are going to move slower. So to get more resolution, you got to run the gel for longer. To get more resolution at a lower voltage, you have to run it at an even longer time period. But as a best practice, run your gel for a long time and at a low voltage. That will make sure that the bands that you see within your gel are nice and crisp and defined from one another. Now, the remainder of these samples from here to here, What I did for this was I simply increased the amount of protein across all of these lanes. So from well number 1 to well number 8, or protein sample number 8, I was increasing the amount of protein. And what you can see, and what I want you to see, is this band right here is common amongst all of these samples. In sample number 1, it's virtually absent. 2, 3, 4, and so on. It seems like the amount of protein increases steadily, and then gradually it kind of continues to increase until we get to sample number 8, where we have the most protein in there. So we're increasing the amount of protein because I wanted you to draw a correlation between amount of protein and being able to visualize something in there. Now, with that said, one of the most important tools or keys for doing SDS-PAGE is being able to calculate the approximate size of a protein. Now, it's a logarithmic scale where you can look at log of the molecular weight of a protein versus migration distance in centimeters. And you can draw a correlation between how far a protein migrates from the top of the gel to a specific location. We have on our molecular weight ladder 2 examples. We've got one protein that's 120 kilodaltons, another that's 95 kilodaltons. These migrate different distances. The protein that's 95 kilodaltons migrates a greater distance from the starting point than that protein which is 120 kilodaltons. Now, what you will put together with this information is a linear curve when you're looking at the log of the molecular weight, and you'll get a y equals mx plus b. And you'd be able to say, well, here are my known proteins, here, 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 here. I have an unknown protein that migrates this distance, this many centimeters. I can then use that number, plug it into my equation, solving for y, calculate the antilog of that, and ultimately determine what the molecular weight of that protein is. And you'd be able to say, okay, well, this protein right here, just as a kind of off-the-cuff calculation, well, it's between 95 and 120 kilodaltons. Let's say it's 110 kilodaltons. Can I say that? Yeah, I can with the amount of information that I've got provided to me. I can make that calculation. Now, how would I get a more accurate calculation? I'll give you a hint. By adhering to these 2 things, by running your delta at a lower voltage and for a longer time period. If I run it for a longer time period and at a lower voltage, I get greater resolution. Then I can say if a 120 kilodalton protein will migrate 6.2 centimeters, whereas a 95 kilodalton protein will migrate 13.6 centimeters. How far did my protein migrate? It migrated 10.6. Then I've got a basis for comparison that I can make a calculation or make a more accurate calculation of the molecular weight of my protein. Okay, so what I've talked about here and what I've discussed, what we've discussed, we haven't discussed anything, but what I've shared with y'all is the details of the stain solution, the details of the de-stain solution, the similarities between the stain solution and our Bradford reagent. In addition to that, looking at a protein gel, what can you resolve based on what's in there? What can you see based on the standards that you've looked at? How could you get a better looking protein gel? Those are all some of the things that we've discussed or that I've discussed in this. At any rate, I hope that you have a good one, and that's all that I got.